That's lovely. I normally give scientific talks and they don't clap beforehand, so that's a really encouraging sign. Thank you very much for coming out. I'm really excited tonight to be here and to talk to you about the signatures of the Milky Way's formation that is captured in starlights and the work that I do. So the field that I work in is called galactic archaeology, and this was a field that was largely founded by my PhD advisor. His name is Ken Freeman. He did his PhD here in Cambridge in 1965, and I'm his 50th PhD student, so there's a bunch of us running around. And the idea with galactic archaeology is we're trying to understand how the galaxy we're in, the Milky Way, has formed and evolved. And this field has been incredibly boosted in the last 10 years by all of the data that's now available that I'm going to tell you a little bit about. So this is how my talk is going to go. I'm going to talk to you about signatures in stars, and then go into what they mean, talk about how they got there, and then there'll be a quiz. But it won't be a high-pressure quiz, it will be a vote to get your input about an experiment that we did and to see what your prediction is. So I hope that that will be a little bit fun. So I'm going to start by showing you a picture of a billion stars taken by the Gaia satellite. And you may have seen this picture, it's extremely famous now. The Gaia satellite has been an extremely important mission for galactic archaeology. It was launched in 2013 and it sits up in the L2 orbit, 1.5 million kilometers from the Earth, and it scans the sky. And it does that continuously. It did that for 10 years. And it scans a little patch of the sky in 6 hours. And over time, it builds up 100 measurements of every object that within its brightness limit. Okay, so this is the picture of the billion stars from Gaia. So this is what we see when we look out into our galaxy. Now we're embedded in it. So it may look a little bit strange to you because we are in the disk. We live in a spiral disk galaxy. And what we're seeing is looking at, in the center of this, let's see if I can get this working, the galactic center. And you see there's all this dust blocking the starlight along the line of sight to us. And this is very much like smoke from a fire. So we can't see through this very well. Okay, now if we were outside the galaxy and we could see it, we'd probably look something like this. We live in a spiral galaxy. We have spiral arms. This is like traffic building up. Okay, it's very similar. These are transient features. They change over time. And our Milky Way galaxy is about 100,000 light years across. So it takes 100,000 years from light to go to one side to the other. And it's about 2,000 light years thick. So it has the dimensions of a plate. And the sun sits about halfway between the center and the edge. Okay? And we have this beautiful bar structure in the middle. And everything's moving. So we know that the Earth rotates, and that's our day, and we know that the Earth orbits around the sun, and that's our year. But the sun and the Earth and all of this whole solar system is going around the center of the galaxy. And it's doing that at 220 kilometers per second. So that means it takes about 230 million years to do one full revolution. So we don't have much sense of that because human timescales are short. But between the time the dinosaurs were here and tonight, we would have done one full revolution. So I'm going to show you the populations that we study in galactic archaeology, and these are the disk. So this is where most of the stars are, and this will be what I'm talking about mostly tonight, the stars of the disk. We also have a bulge, and this is seen face on in this other galaxy. The bulge in the Milky Way is this bar structure. The stars are orbiting in very special orbits in this region. So everything is moving. The stars on the disk, like the sun, are moving in circular orbits, and the stars in the center region trace out this structure that supports the bar. One of the protagonists of my talk tonight will be open clusters, and these are like little stellar nurseries. They're little groups of stars in the disk that are born together, so they're stellar siblings, and they're really interesting benchmarks to study. There's also the stellar halo, not the dark matter halo, but the stellar halo. About 1% of stars are in the stellar halo. They're a very interesting population. They represent the building blocks from the earliest times in the galaxy's evolution, but I won't be talking about them tonight. They have these eccentric orbits, but apart from that, I'll focus on the stars of the disk. There's also external galaxies that we see in the Gaia image, and I want to briefly pause on external galaxies to show you one of my favorite images. Now, this is very old in the sense of it's taken from the Hubble Space Telescope. It was taken in 1995. It's the Hubble Deep Field. And then we've only known for 100 years, which is pretty short on human timescales, that there are other galaxies. And there are billions and billions of other galaxies. And I think this is the most profound view of that. So with the Hubble Space Telescope, they pointed it at a blank patch of the sky for 100 hours. Now with our eyes, we're constantly refreshing on the fraction of a second, so we don't see this with our eyes. But if you point the telescope at a blank patch of the sky for 100 hours, it just counts up the photons. And when it does that, all of these galaxies are revealed. So you'll see that all of these galaxies are different colors, sizes, shapes, and the light has traveled billions of years to reach us. And one of the points I'd like to make is there are other spiral galaxies. If you look, you can spend a long time looking at these sort of images, you can make out spiral galaxies that are probably very similar to the Milky Way. So in galactic archaeology, one of the things that we're doing is working to understand the Milky Way because we're understanding galaxies in the universe in general. So what I'm talking about tonight is signatures in stars, and in particular, signatures from something called the photosphere. And that's the stellar surface. That is the part that we see. And I'll be talking about photons. That's the light that we see from stars. And a very important property of this light is it has a wave-like nature. Now this is the sun. This is the most important star for us, of course. But stars come in lots of different sizes and masses. The sun's a little bit higher mass than the average star in the Milky Way galaxy. And stellar masses can range from about 10% of that of the sun to, I've learned today, I thought it was a few hundred, but apparently 1,000 times that of the sun in the early universe. Stellar radii are something that can be quite variable. Stars can range in their radius from 10% of that of the sun all the way up to 1,000 times of that of the sun. And the sun is going to evolve as it ages and its radius will change. So the radius of stars is something that changes over time. The sun is going to grow to 200 times its current radius in about 5 billion years. So the main concept of my talk to understand the signatures of stars is shared with grocery shopping. So I want to briefly pause and talk about grocery shopping, because if you can understand grocery shopping, you can understand everything about spectroscopy and galactic archaeology, as far as I'm concerned. So the idea of grocery shopping, so we're on the same page, is you get your trolley and you walk along the aisle putting your bits and bobs in, and then when you try and leave, you're confronted with one of these self-checkout machines. And the goal of this self-checkout machine is you have to find and scan these things. Now, do they look like this here? I'm getting noise. In Australia, they're all 2D barcodes. I took a photograph of an object of food in my room, and the barcodes look like that. But yeah, that's why yeah. So, but they're essentially, these are barcodes. The whole premise of a supermarket is that each item has its own unique barcode. And when you scan that, that tells you how much the thing costs. Okay, and then you're allowed to pay and leave. So I want to use this idea of barcodes and take that idea of barcodes to the night sky. So if you go to Australia, you go to a dark place and you look up, the night sky looks something like this. So we basically get the Gaia image overnight. It doesn't quite look as dramatic in Cambridge, but I tried to take a real photograph of the stars, but every time I went out it was cloudy. So I took this one off the internet. So perhaps it looks something like this. So you might be very underwhelmed by stars. You might think, well, they're just dots. But what we can do is we can go to telescopes, and this is one of the telescopes at the Siding Spring Observatory in Australia. It's a 4-metre telescope, and similarly to the Hubble Deep Field, we're going to be able to learn more about stars with our telescopes. So how those telescopes work, how this one works, it's a 4-metre mirror, and you point that at the sky where the stars you want to observe are. And we know where these stars are because the sky is basically like Google Maps. Stars all have their coordinates. Missions like Gaia gives us the coordinates of stars, so we can type in their coordinates into the telescope and it will go and observe them. So light from the stars comes into the mirror, that's then reflected to the primary focus. And sitting at that primary focus are some optical fibres. And that light travels down optical fibres into some instrumentation called a spectrograph. And what that spectrograph does is it organises the light. Now once you organise anything, you start to make sense of it, whether it be your cupboard or your calendar or light, you start to get more information out of it. And that's exactly what we're doing here. So when we put light through our spectrograph, it spreads it out into its component wavelengths, from the shortest ones to the longest ones. And then we look at those wavelengths and we count up how much light we observe across each wavelength. So now I'm showing you the same 3 stars, and what we have is our shorter wavelengths here, our longer wavelengths here for each star, and if you look at the photons or the light, it's all got this funny shape, and it has this funny shape in different ways for different stars. And these are our stellar barcodes. So I'm going to tell you about what information is in stellar barcodes and how we use that to run experiments on the formation of the galaxy. So the galaxy has 200 billion stars, and we certainly have not observed all of them, but we have spectra or barcodes for many millions of them. And the reason that we have this is there are international teams all over the world with telescopes continually observing these spectra, such as the setup that I just showed you. And some of these are run out of Europe, like the Gaia mission, Gaia ESO. Some of these run out of China, the Lamos survey. Apogee is an American survey, and Galar is an Australian survey. So this is really an international endeavour. So we can use these barcodes to measure what stars are made of and understand our origins. So what barcodes tell us about, what information they contain, is they tell us about elements. Now this is probably familiar. Is this familiar? Yeah, good. Okay, good, the periodic table. So the periodic table just organises all of the building blocks of matter, building blocks of stuff, in order of increasing atomic number. So everything, all of these elements are made of building blocks themselves. They comprise protons and neutrons and electrons. And we just organise them from increasing number of protons, from the smallest to the highest. And the colour is what I'll come to in a moment. So if we didn't have elements, everything would look like this. It would be very sad. We don't exist. So elements are really important. I just want to run through the exercise of figuring out how many elements are easy to find in the room tonight. So anyone want to guess how many elements I can easily find in the room? 10? Yeah, what do you reckon? 25, good guess. Another one? 100, good. I'm liking having, any more guesses? Yep. 67. Wow, that is very specific. I love that, thank you. Those are really good guesses. I'll show you there might be a different number, more than what I found. I'll just show you what I found. So in ourselves coming tonight, we have about 20 elements. Okay, we're comprised mostly of oxygen, carbon, hydrogen, and nitrogen. But we've also got a lot of other stuff in us. We have things in our muscles, in our bones, in our blood, in our lungs, in our skin. And so just in coming here with ourselves, we brought 20 elements. There's more than us in this room. We brought our laptops and our chairs they're sitting on. We didn't bring them, but we're using them. They're our clothing, our jewelry. Most people probably have a phone. And now we've easily gotten up to 50 elements. And these are the ones I could easily find. There's probably more. So if you don't believe me, let's just take a little look in more detail. Everyone's probably got some lithium in their batteries. There's probably a little bit of beryllium in your phone, these intermediate things. Iron, aluminium are in the furniture. Things like copper, cobalt, nickel. They're in electronics and wiring in the middle here. Okay. If you have jewelry, you probably have silver, gold, maybe platinum and zirconium. And all these bottom things, they're really important for our phones. They make our phones look nice and shiny. They've got nice magnetic properties, so we can put them in our speakers. Okay, so we brought all of this stuff with us tonight. And what I love about my job is that I am always thinking about the fact that we brought the history of the universe as well as the galaxy and everything we are and everything we touch. So all of these elements are created in stars and at the beginning of the universe for the lightest elements. So hydrogen, helium, a little bit of lithium, beryllium are created at the beginning of the universe. And then everything else, we have a little bit of boron, beryllium created in cosmic ray fission, these intermediate things created in explosions, and these heavy things, all the stuff that goes in your phone, for example, they come from merging neutron stars, which are an incredibly beautiful exotic event. So to understand how these elements got into stars, we just need to go through 4 concepts. The beginning of the universe, gravity, stellar life, and stellar death. I don't have anything to say before the beginning of the universe because we don't have a theory for that. We only have the theory for the initial conditions that represent the Big Bang, where the universe expanded from a hot, dense state. So at the beginning of the universe, at the Big Bang, the universe expanded from its hot, dense state and formed the lightest elements in a process called Big Bang nucleosynthesis. So this formed hydrogen, helium, a little bit of beryllium, and lithium, and all of this stuff was in the form of gas. Okay, so let's look at gravity. You've probably heard of Isaac Newton and being inspired by an apple falling from a tree here at Cambridge and having this realization that gravity is a force of attraction between two objects and increases with their mass and decreases with the distance between them. That was in the late 1600s. In the early 1900s, Einstein came along and understood gravity as a consequence of massive objects curving space-time. And that bends the light, that bends the path of light and other objects around them. And that forms general relativity, which was published in 1915. So whether or not you want to think about gravity as this force of attraction or in the more complete framework of general relativity, the point is gravity causes mass to come together. So if you have gravity and gas, you have star formation. And this is one of my favorite images from JWST. This is the pillars of creation. This is somewhere where stars are forming because gas is collapsing due to gravity. So that gas is collapsing and it's all dusty and you can't see through a lot of it. You can see it's eroded because there's these very high mass stars just out of view, these very young stars that are producing all this UV radiation and eroding these pillars. And what you can see is there's little red stars here. Those are our little baby stars that are forming. And so inside these pillars of creation, there'll be lots of individual open clusters. And these are groups of stars forming together with maybe 100 stars in them. And this is the cartoon version of what's happening as these stars are forming. So our gas is collapsing, clumps are forming, and our protostars form. And the definition of a star is when fusion begins. So in the middle of a star, it's very hot and dense, and that causes lighter elements to crash into one another and form heavier elements. So the sun is fusing hydrogen into helium, and that's releasing its energy. And more massive stars will fuse heavier and heavier elements, climbing the periodic table all the way up to iron. Okay, so fusion is this nuclear process in which light atomic nuclei combine to form a heavier nucleus, releasing energy. And that's what causes stars to shine. Now, young stars have these disks, and that's leftover material from the star formation. And a really beautiful part about star formation is that planet formation is a ubiquitous part of that. And I'll come briefly to planets. I don't study them, but it's certainly something that we think about. Now, there's something missing from this picture, and that's the point that this is iterative. So what happens is that stars have finite lives. They are born and then they die. And they die in different ways, according to their initial mass and whether or not they have a companion. And when they die, they eject the elements that they make in their cores or that they make in the explosions. And that goes back into this gas. And we get the next generation of stars forming out of this enriched gas. So we're gradually enriching the galaxy in heavier and heavier elements, and more of these elements from the periodic table because of this cyclical process. This is about the most technical slide of my talk, where I'm going to basically talk to you about the different ways that stars re-enrich the universe at the ends of their lives, because this is quite diverse. And there are 4 classes, but there's variability within each of these classes. But the general idea is, when you have a high mass star, so something maybe 20 times the mass of a sun, it's going to fuse heavier and heavier elements in its core all the way up to iron. So it will go hydrogen to helium, to carbon, to oxygen, to sodium, to magnesium, to neon, to silicon, to iron. It can't fuse iron into anything heavier. So what's going to happen is gravity is going to take hold because there's a force that way, but no energy pushing out that way. That core is going to collapse. It's a really massive star. It'll collapse into a black hole. It's about 20 solar masses. It'll collapse and form a neutron star, undoing all of those fusion efforts. So as it does that, as that core collapses, it causes a shock wave to go out and explode the whole star, okay, releasing a bunch of elements. So you have this neutron star left over, and this is a small thing about 10 kilometers across, extremely dense. Probably a teaspoon weighs about 5 million elephants. And so if you have a situation where you had 2 exploding stars and they're in a binary, and we see binaries, these binaries exist, you can end up with 2 neutron stars that are in spiraling. They're losing energy due to something called gravitational wave radiation. They get really, really fast. As they get closer and closer, they smash into one another, explode, and we put all the stuff in our phones. Okay. The sun will become a dying low-mass star. Okay, in about 5 billion years, it's going to go through this process of fusing hydrogen to helium, and then helium to carbon and oxygen. But it's not massive enough to be hot enough to make that carbon and oxygen fuse into anything heavier. So what's going to happen is that the outer layers are just going to blow off when it runs out of energy, very gently, fade gently into the night. And then we'll be left with a white dwarf, this thing made of mostly carbon and oxygen. And again, if we had a situation where we started off with a star in a binary system, and you end up somehow with a white dwarf and another star that's still in its nice star phase, that white dwarf has a maximum mass called the Chandrasekhar mass. And if you exceed that mass, because a little bit of the material from its star, its companion star, goes onto the surface, then it will explode in a big boom. And that will release a lot of iron, like the iron in our blood. So that's how stars re-enrich the universe. So stellar spectra are barcodes, and they encode the amount of elements in stars. So now I'm showing what you saw before, these stellar spectra with the dips sorted in wavelength. Excuse the angstroms, we should be working in SI units, but sorry about that. And we can see that all of these dips, my laser pointer has decided it will be no more. All of these dips correspond to different elements. I've got one more technical slide before our quiz that'll go through why these different wavelengths correspond to different elements. Now, these barcodes exist because of the strict rules that atoms obey. Now, when I went to high school and university, probably because I did an engineering degree, not a physics degree, I learned the Bohr model of the atom, which is a simplified model of the atom. Is other people familiar with the Bohr model of the atom? It's this idea where, so let's use hydrogen. You have a proton and an electron, and you have your proton in the nucleus, and the electron can exist in different orbitals around it. So I would like to replace this with the wardrobe model of the atom. So in the wardrobe model of the atom that I've invented, the person is the proton, and the electron is all of the different outfits that the proton can wear. This is how a hydrogen atom behaves. It can wear lots of different outfits. So this shows, technically, this is a solution to the Schrödinger equation, a wave function of the electron. But what it also represents is a hydrogen atom and its different outfits. And a hydrogen atom can change outfits, but it can't change outfits for free. It either has to absorb a little bit of energy or give up some energy. So if you're sitting in a stellar photosphere, if you're a hydrogen atom or any atom in a stellar photosphere on the surface, there's lots of energy to absorb those passing photons. So if we now focus on a hydrogen feature in the spectra, what's happening is the hydrogen atom is changing from one outfit to another. And all the hydrogen atoms, lots of the hydrogen atoms are doing this. And they block a little bit of the light because they absorb a little bit of light to enable them to do this. And they all do that at one wavelength that corresponds to the energy of the photon that they're absorbing. So those line depths that we're seeing, we can work out from the line depths how many of all of the elements are there. And all of the different elements will have these absorption features, these dips at different wavelengths. So stellar spectra are barcodes. This is the same slide as before. They encode the amount of elements in stars. And what we see in the stellar photosphere is the stuff the star was born with. This fusion happens in the core, but that's isolated from the surface. The surface is this gas that captures this re-enrichment of the galaxy over time. So that means that we can turn these barcodes into real measurements of how much stuff every single star is made of. And this is the sun. We have the symbol, the name, and the fraction. So it's only a couple of the elements to make the point, but the sun has 71.5% hydrogen, 27% helium. We're almost at 100%. So the rest of the stuff we call metals because this other stuff is the stuff created in stars. And for something like the sun, it's only about 1%. It's 1.5%. But stars will range from a fraction of a percent up to 5%. Okay, so that's the amount of stuff that's metals. And all of these fractions of these metals can vary. So now we're getting to our experiment, our doppelganger test. Does anyone know, everyone knows what a doppelganger is? Yeah, so there's doppelgangers in people, And this BBC article leads with, "You're surprisingly likely to have a living doppelganger." They then go on to say, well, the chances of sharing 8 dimensions with someone else is less than 1 trillion, so that's not likely. But if you mean looks a bit like you, then probably we all have a doppelganger. So the experiment that we're going to do now that we have all these barcodes for millions of stars, is we're going to do a doppelganger test on stars. We're going to ask how similar in barcodes are random pairs of stars, so strangers, compared to birth siblings. And our birth siblings, we know where to find them. They're in open clusters, like in that Pillars of Creation image from JWST. We're going to have a little metric, our barcode distance between pairs of stars. We're just going to take lots and lots of pairs and do the barcode of star 1 minus the barcode of star 2. We're remembering those barcodes tell us all about the elements that are in the stars. And we're going to do this for 2 groups of stars, our open cluster stars, they're our birth siblings, and random pairs, completely different places across the disk, lots of random pairs. Now, because we're going to vote on what you think we're going to find, I better be accurate. So I should say the measurements are precise to 5%, it's like these pharmaceutical ads. Measurements are precise to 5% and a fixed overall metallicity fraction. So the total metals is going to be the same for all pairs. The amount of metals can vary from a fraction of a percent to about 5%. So we're going to do one condition where we say, well, the total fraction has to be the same. So this tests the diversity in the elements, in the barcodes, at a fixed metal fraction. So I'm going to go through these, ask for a vote, and I'll tell you what astronomers thought before giving you the answer. So the first is A, all stars are unique. B, doppelgangers occur, but not often. So like in humans, it becomes viral when doppelgangers find one another. Or C, there's lots and lots of doppelgangers. So who votes we're going to find A? One person. Good, that's good, good. Who votes we're going to find B? Oh, we have a big showing for B. Who votes we're going to find C? Wow, well, I can tell you what astronomers thought, A. So you're representing astronomers. And we're about split 50-50 on B and C, and I can tell you what the answer is. The answer is C. We discovered that lots of stars have the same barcodes. So this shows a sort of example of what this looked like in the actual analysis. We have our barcode distance, and we're looking at the number of pairs that have this barcode distance. So our open clusters, our siblings, will have small barcode distances because they're very similar. And our field pairs, our strangers, have bigger barcode distances because they're more different, but there's this big overlapping region. And this overlapping region, they're our doppelgangers. And if we do the maths, and it turns out that there's 1 pair in 200 doppelgangers, and maybe you think, oh, that sounds like it's not that common, but you only need 21 stars to get to more than 200 pairs. So that's an extremely high rate of doppelgangers. In about every 20 stars, you're going to have these doppelgangers. So I want to bring this back, as we get towards the end, to the idea of us. Now, if we put this in context, this means there's lots of other suns. There's about 1 million doppelgangers of the sun, stars that are exactly like ours. So the processes that have built us and built the sun we orbit and its family of planets might well be replicated elsewhere. Now, we still do not know how life arises. We certainly can't make conclusions about other life on other planets if these conditions are more favorable to life. But I think it's a very interesting discovery. And we know that other planets are forming around stars. This is an example from the ALMA telescope, or the ALMA instrument. And it shows a T Tauri star. This is a young star with one of those protoplanetary disks. And we can see a planet forming in this dot. So we see planets around stars. And there are about 6,000 known exoplanets. And there's a new mission coming that's going to find a lot more. So in the future, one of my hopes is that we'll better understand this the simplicity, gone crazy, the simplicity of abundant space and planets. So the lack of complexity, if there is one. So my conclusions are that we've discovered that many stars in the Milky Way are doppelganger, and this is not just a nice statistic, but it could be a signature of formation and possibly our origins. And this was a surprise because astronomers expected this really high dimensionality, and that's just not what we found. And the result's really a simplicity hidden in what otherwise might appear to be overwhelming complexity. And this is a very personal lesson for me. When I started as a baby astronomer and I had all these spectra that I had to analyze, I was overwhelmed. I thought, this is so complex. How do I make sense of this? And I realized that you start to reach understanding and making sense of it when you can find that simplicity that underlies these data. And let me end with the idea that this underlying simplicity that we found in the galaxy is really ubiquitous. So from one perspective, our Earth is incredibly complex. There's 70,000 types of trees and thousands of different yogurts, and there's 8 billion people. Yet when I show you this image, I'm sure you all recognize this first row as trees, and you can differentiate them, trees, straight away from yogurts. And if you decide to meet your friends in a crowded place, you can find your friends against strangers without any trouble at all. And there's 2 reasons for this. Well, one is our brains are just amazing pattern recognition machines. But the second is that our brains are able to do this because there's underlying simplicity that they're tapping into. So this is something that we find everywhere. So thank you very much for coming. It was a lot of fun to talk to you tonight.
Wonderful. Do we have any questions for our speaker? What do you think? I'm just going to open the door for this gentleman so we can escape. Okay, questions for our speaker at the front, please. Yes.
I was just noticing there with the spectroscope of the sun.
Yep.
The question occurs to me is why isn't there the series of the periodic table replicated in the spectroscope?
Excellent. So we don't measure every element in the periodic table. We only get spectra over a fairly narrow region of the energy or the photons that the sun puts out. So we can't access all of the elements. We access about 40.
But I noticed that lithium and iridium and so on, the early part of the series, they were absent, so they're not accessible.
We do get lithium. We do get, but beryllium is very hard to get. So yeah, a lot of them are not accessible in a lot of our data because they're too weak. The lines are too weak due to the quantum mechanics of the atoms, basically, the way they behave. Yeah, good question.
Wonderful. Any more? Yes, in the middle, please.
Yeah. Thank you for a very nice presentation. I had one question on, so you had the table for the sun and saying this is the percentage of elements in the sun, and down there is atom, 0 point something. Now, my understanding is that heavier elements are concentrated on the nucleus of the sun, towards just by gravity.
Yeah.
Now, how can you observe the spectrum for heavier elements, and how can you reduce the percentage of the mass of the sun or of other stars?
Yeah. So there is a process. The heavier elements over the lifetime of a star will settle due to gravitational settling. They'll settle and go more towards the center. But the center, the core where the fusion is happening, is isolated from the surface. But there's a process in the outer region where you have convection. You have a constant mixing. So what happens is that you still have plenty of elements, even in the very surface of the heaviest elements. So one of the things that happens, though, is they can decrease over the evolution of a star's life due to falling to the center. And we measure that by measuring these open clusters and stars at different points in the open cluster to see how much they've decreased, these heavy elements have decreased. It's a little bit. Does that answer your question?
I'm a bit puzzled in the sense that, yes, I can understand that. I can accept that we can detect elements.
Yeah.
But how can you translate the spectrum into percentage of the mass? Because those processes seem to be very complex.
It's because we have theoretical models. It's because we model the overall things that control the flux. So these are huge computational models. Yeah, of the physics.
It's based on some theories.
Based on, that's right, exactly right, yeah.
Please.
In the cases where when a star collapses onto itself and a black hole is formed and light cannot escape, how do the elements change? How is the spectrography of
So we don't get elements from the black hole, but we get elements from the explosion that creates it. So a black hole does not contribute to, because nothing can escape and there's no matter around it. So it doesn't, but yeah, that's a good question. They don't give us elements, they just take everything.
The back, please.
So out of curiosity, in the open clusters, you were talking about how how the regeneration cycles end up with heavier elements, etc.
Yeah.
What's the kind of spread of life of ages within of generations within a particular open cluster? Are they all fairly synchronous at the same time?
Yeah, that's a good. I always consider open clusters as being the same age because I think they're the same age within the precision to which we can measure them. But they're so the stars themselves, of course, go from baby stars up to the age of the universe. But in terms of the actual age spread within a cluster, I assume it would be tens of mega years. Do you know the answer to this? Maybe hundreds of.
I don't know, I'm a galaxies person. That sounds about right.
Yeah, it's tens to hundreds of mega years. Because otherwise they're assumed to be just formed together. But there is some, you're right, there's some deviation, standard deviation in that.
It's maybe time for one more. Anyone got one more? Okay, yeah, Jennifer, sorry.
Sure.
Yep.
I was just wondering, what status, if any, does the steady state theory now have in terms of origins of the universe?
I'm going to hand that one to you.
No, it's fine. So yeah, the steady state theory is more or less dead, right? So for anyone that doesn't know, the steady state theory was the competing theory against the Big Bang back in the 30s and 40s and 50s. The steady state theory was a Cambridge invention, actually. So you were all in the Hoyle lecture theatre, and it was Fred Hoyle who came up with the steady state theory. The problem was that Hubble saw the universe expanding. He saw galaxies getting further and further and further apart from each other, and that kind of implies there's like a beginning point that kicked off the expansion. But lots of scientists didn't want there to be a beginning of the universe for like philosophical reasons. So Hoyle came up with this theory that the universe kind of expands, everything gets further apart, but then new stuff gets made to fill the gaps, and then that gets apart, and then that just kind of goes on and on and on forever. It's a way to have a universe that looks like it's expanding without a starting point. But then the problem was we discovered this stuff called the cosmic microwave backgrounds, which is like the echo of the Big Bang, right? It's the first light in the universe. That came from when the universe was really young and small and hot, and that can only exist because of the Big Bang. So yeah, so basically since the 1960s we've known that the Big Bang is true, and that pretty much killed the steady state theory dead.
I thought that Hoyle later and Bonley, they tried to bring about some sort of reconciliation between them.
Well, he tried and failed. I mean, so Hoyle, like Hoyle, it's almost a bit sad actually. Hoyle never accepted the Big Bang.
No.
I mean, the whole field passed him by. He spent the rest of his entire scientific career denying the Big Bang. He even tried to come up with the theory that the CMB was the energy produced by this matter, being created in the gaps left behind. Yeah, I mean, I think even very brilliant people can be stubborn and wrong, right?
I think he had to go at Archaeopteryx too, didn't he?
He had to go at many things. He went off the rails. I think there's a species of senior physicist that goes off. No one in this department, of course. Okay, I think tea and biscuits awaits, followed by the planetarium show. Can we thank our speaker again, please? Wonderful.
Oh, thank you. Thank you. Oh, wow. That's true. You're getting it streamed live on the internet.
Oh, yeah, you were.